So last class we have discussed about the IV infusion. First class we discussed about the IV injection. Next we are moving on to the extravascular administration of the drug. So when we are speaking about extravascular administration of the drug, there are two type of absorption model are possible. That is called as the first order absorption model and the zero order absorption model. And in most of the cases, the plasma drug concentration versus time frame profile can be described by one compartment model with first order absorption and first order elimination. But in some cases, it is better to describe by assuming zero order kinetics. So this zero order absorption is characterized by constant rate of absorption and is independent of the amount remaining to be absorbed. Okay, so this absorption can be first order or a zero order absorption, and usually the zero order absorption is characterized by constant rate absorption. That is nothing but or similar to the IV infusion, we can say zero order absorption, or the zero order absorption model you can draw, that is similar to IV infusion. The same model you can draw it again. So it's given as zero order absorption. So we can write it as drug at extravascular site, then rate of infusion are 0, then blood and other tissue and elimination. So it is similar to IV infusion. So it is called as the zero order absorption model. Okay, the same model you can draw, and all the parameters what you have derived under the infusion can be given. Then the first order absorption process. So first order absorption process means there is a decline in rate with amount remaining to be absorbed. The decline in rate with amount remaining to be absorbed. That is, the absorption rate depends on amount remaining to be absorbed. The absorption rate depends on the amount remaining to be absorbed at the absorption site. Okay. So the model, only the difference is the above one, it is drug at extravascular site and R0, that's the rate of infusion. But in case of first order absorption, we can say drug at extravascular site, there is a absorption rate constant Ka, then blood and other tissue, and then the elimination Ke. I also told you the decline rate with amount remaining to be absorbed. There is a decline in the rate with amount remaining to be absorbed. That is, the absorption rate depends on ARA. So you can plot the ARA versus time graph. So ARA, the amount remaining to be absorbed versus time. So if you get a curve, you can say it follows first order. If you plot ARA versus time, and you will be getting a straight line. If you are getting a straight line, then it will be zero order. This is the normal graph. This is the normal graph that is plotting ARA versus time. In the normal graph, if you get a straight line, it follows zero order. Okay. Next is the log plot. This is log ARA. That is a semi-log plot. So this is the log ARA versus time. So in the log plot, if you get a straight line, if you get a straight line, it follows first order. Okay. The normal graph, the first order, you will get only a curve, but in the log plot, if you get a straight line, you can go say it follows first order. So in the log plot, usually for zero order, you will get a curve. You will get a curve. So that's thereby you can differentiate zero order absorption model and the first order absorption model. So zero order absorption similar to infusion. The first order, that is after extravascular administration of the drug. So now we will be concentrating more on the one compartment model for extravascular administration, that is also called as the first order absorption model. The question may come, explain and derive first order absorption model. Then you have to write one compartment model for extravascular administration. Or sometimes you will get explain the zero order absorption model. Then you can write up the zero order absorption, you draw the model. If the parameters required, you can just explain that infusion. Same thing. Okay. So this is a one compartment model for extravascular administration. So first step will be the model. You have to draw the model, drug at the extravascular site, rate of absorption Ke, blood and other tissue, and only the elimination Ke. So after extravascular administration, the drug gets absorbed and reaches a maximum, then slowly decreasing concentration of the drug, and finally absorption becomes zero. This we know. After oral administration of the drug, if you plot a graph, that is plasma drug concentration versus time, then the absorption slowly increases, reaches a maximum, then post absorption, then only the elimination. That's the graphical representation. Then the plasma drug concentration versus time profile is characterized by this graph is characterized by different phases. There's absorption phase, maximum concentration, post absorption, and elimination. So it is characterized by different phases. First one is called as the absorption phase. So in the absorption phase, we can see gradually the absorption increases. So we can say the rate of absorption is greater than rate of elimination. We are comparing with these two, absorption and elimination. So at the absorption phase, the rate of absorption is much greater than the rate of elimination. That is denoted by d by dt into dBEV. That is the rate of absorption, the amount of drug absorbed through extravascular route. d by dt into dBEV is greater than d by dt into dBE. That is the amount of drug eliminated. So this absorption is greater than elimination at absorption phase. Then at C maximum. So at C maximum, we know that it's a maximum concentration, means at that particular point the rate of absorption is equal to rate of elimination. At the peak point, the rate of absorption is equal to the rate of elimination. So we can write dBEV is equal to d by dt into dEE. Next, the post absorption phase. The post absorption phase. So we are comparing with two parameters, rate of absorption and rate of elimination. So the rate of absorption is less than the rate of elimination, means d by dt into dEV is less than, it should be less than the reverse direction, okay, less than d by dt into dBE. Then the last one is the elimination phase. Elimination phase, the rate of absorption is, there is no absorption at all. So the rate of absorption is 0. So we can write d by dt into dBEV is equal to 0. Thereby we can denote like that. So absorption phase, d by dt into dEV V is greater than d by dt into dBE. At Cmax, this d by dt into dEV is equal to d by dt into dBE. Then at post absorption phase, d by dt into dBEV is less than d by dt into dBE. And at elimination phase, this d by dt into dEV is equal to 0. So to draw the model, then give the graph and explain all these four phases. That's the introduction part. Then the derivation. So the rate of, first step always will be the rate of change of amount of the drug present in the body is equal to the rate in minus rate out. It's the rate in minus rate out. There is the rate of absorption and the rate of elimination. So you can write dB by dt is equal to the rate in Ka into dBA minus Ke into dB. That's equation 1. So this is the rate in, this is the rate out. dBA is the amount of drug at absorption site remaining to be absorbed. So next step will be the integrating the equation 1. Got the equation 1, we are going to integrate the equation 1. So after integration, you will get the amount of drug present in the body is equal to K into F into D0P divided by Ka minus Ke into e raised to minus Ke into T minus e raised to minus Ka into T. Okay, after integration, you will get a final equation. This equation, how to by heart it. After integration, we will be there directly writing the equation. So this how to by heart it. That is dB is equal to K into F into d0b divided by Ka minus Ke into e raised to minus Ke into t minus e raised to minus Ke into t, where this F is called as the fraction of the drug absorbed and d0b is the initial amount of the drug. d0b is the initial amount of the drug. So we got the amount of drug present in the body that we have to convert into its concentration term. Okay, for that again we will be using the relationship that is dB is equal to Vd into C. Using the relationship that is dB is equal to Vd into C. So you can write C is equal to dB by Vd, or this equation divided by Vd will give you the concentration term. Now substituting that, so you will get concentration C is equal to K into F into d0b divided by Vd into Ka minus Ke into e raised to minus Ke into t minus e raised to minus Ka into t. So we got the derivative equation, that is a concentration of the drug administered extravascular following one compartment model. This we got an equation for concentration, that is C is equal to K into F into d0b divided by Vd into Ka minus Ke into e raised to minus Ke into t minus e raised to minus Ka into t. So this is the initial part, that is what do you mean by zero order absorption, first order absorption. How can you differentiate with the help of the amount remaining to be absorbed versus time graph? From the normal plot and the semi-log plot, we can differentiate first order and the zero order. And the one compartment model for extravascular administration, we have to draw the model. Then the graph, we have to explain all the four phases, we have to explain. Then the basic derivation, that is rate in minus rate out. So finally you will get C is equal to K into F into d0b divided by Vd into Ka minus Ke into e raised to minus Ke into t minus e raised to minus Ka into t. So we got an equation that is a concentration of the drug after extravascular administration following one compartment model is given by the equation 3, that is the C is equal to this equation. Next will be the parameters. What are the parameters to be determined? The important parameters are the Cmax, that is the maximum peak plasma concentration, and the time corresponding to the peak plasma concentration, that is Cmax and Tmax. These are the two important parameters after extravascular administration, that is Cmax and Tmax. We can find out. Then from the graph you can see in the model there is absorption rate constant and elimination rate constant. That also you have to find out the elimination rate constant Ke and the absorption rate constant Ke. All these four parameters also has to be find out. These are the parameters after extravascular administration, that is Cmax, Tmax, elimination rate constant Ke and absorption rate constant Ka. Okay, we will discuss in the next class.